Okay, now that we've reviewed some properties of the PDF and CDF for a continuous random variable, let's take a look at how we can calculate the mean and variance for a continuous random variable. We've done these calculations for discrete random variables, and so we'll see that the definitions are pretty much the same, just the way that we calculate things with continuous random variables are with integrals as opposed to with discrete random variables where we're summing up a bunch of things. So if you recall, when we talked about the mean or the expected value for a discrete random variable, we said that this was equal to the sum of x times the probability that random variable x is equal to that. And we summed over all values of x. And so when we're doing this for a continuous random variable, now x can be any value, not just integers. So that's where we get this integral calculation. So the expected value for a continuous random variable, really we just changed this sum to an integration symbol. And so we're going to integrate over all of the possible values of random variable x. So that might be that we have improper integrals. More typically, we start at the minimum possible value of x and we stop at the maximum possible value of x. And these might be finite values. But what we're going to integrate is the value of x times the value of the PDF at that value of x. So in some sense, again, we're calculating x times the probability of how likely x is, and then we're adding up all of these contributions. So it's the same formula, just now we're going to integrate instead of sum up values. And with that in mind, the variance is also going to be defined the same way we defined it with discrete random variables. It is going to tell us the expected value of x minus mu squared. So what this means, in some sense, the variance is measuring on average how far are values of the random variable from the expected value of that random variable. So the variance is measuring, in some sense, the average distance of points from the mean. So it's telling us something about how spread out the values of this random variable are. And so one way we can compute the variance is by using this expected value formula that we have up here, except instead of taking the expected value of x, we're taking the expected value of x minus mu squared. So this could be calculated by integrating from the minimum value up to the maximum value of random variable x. And we're going to integrate this product. So we're going to take x minus mu, which you would have to calculate the expected value first before you calculate the variance. And then we could multiply this by the probability density function and get it that way. These typically are quite messy integrals to solve, you can imagine. So we've shown that we have this nice property for calculating the variance, at least in the discrete case, where we can calculate this by taking the expected value instead of x squared and then separately subtract the expected value of x squared. So the squared here is in different places. So here we're taking the expected value of x squared. So that would look like this. And over here, we're taking the previous expected value that we found and squaring it. So that would look like u squared. So typically, after you find the mean value up here, then what you would do is calculate the expected value of x squared and then take the difference of these two values. And another descriptive way of describing the data is with what is called the median value. So the median value is a value of x such that when we integrate from the minimum value of this random variable up to that value of x, we should get 1/2. And this 1/2 corresponds to what is the probability that random variable x, sorry that this is a capital random variable x, is less than this particular value of x. And so another way that we could describe this is saying we want to find the value of x such that 50%, one half of the values are less than it. So really, this is going to be the value of the random variable that divides the data in half. So half of the values of x are less than it, half of the values of x are greater than it. And so let's take a look at how we can visualize the median from a graph, either of a PDF or a CDF. So using the example that we had last time, which was, say, the weights of squirrels, here we have the PDF on the left side here. And so the median, in this case, we can see would be the value 9, since 9 divides the total area of this graph in half. It's not going to always be this nice to just observe it directly from the graph. But in this case, for normal distribution, we can actually see that right in the middle here, this is the median. So the area over here is 1/2. Instead, if we were given information about the CDF, then we would want to figure out when is the CDF equal to 0.5. So depending on whether we have the PDF or the CDF, this might look, how we find the median might be a little bit different. But at the end of the day, this value is representing the value of the random variable is 50% of the values are less than it and 50% of the values are greater than it. And so on this last slide, I want to take a look at an example so we can practice doing calculations such as the mean with a continuous random variable. So let's consider the following example. We have some random variable x, and its probability distribution or its probability density function is given by this piecewise function that if x is between 0 and 4, the probability density function is equal to x divided by 8. If x is any value outside less than 0 or greater than 4, then its value is 0, meaning the only possible values for random variable x would be between 0 and 4. And so let's first think about how we could sketch a graph of the PDF, how we could use that graph to construct a graph and find a formula for the CDF, and then how we can use information from the PDF or the CDF to do some calculations, like calculate the probability that x is less than 2, calculate the expected value or the median. And so to answer question 1, sketching the graph of the PDF, this function is a linear function, right? So its slope is 1/8. So the graph of this should look like a graph of a line whose slope is 1/8 over the interval from 0 to 4, and otherwise its value is 0. So technically speaking, at this break in the graph, we have a closed point here and an open point over here, since it is possible that random variable x is equal to 4. So the inclusion here is there. And you could check and just verify to yourself that the total area beneath this graph, if I were to calculate the triangle area beneath this graph, that should come out to 1, since the total area beneath this graph should be 1. And so if we want to find a formula for the CDF, recall that the CDF is the antiderivative of the PDF. So I can integrate this from its minimum value up to whatever value of x I want to specify. And what I would integrate would be the PDF. And so I changed the value here to t because in the end, the upper limit of the integral corresponds to the value of the random variable x. So since I used x in the upper limit, I should use a different variable inside the integral. And so for this, we can integrate this, and here we would get t squared over 16 from 0 up to x. And now when we evaluate this, we get x squared over 16. So the CDF, we can find a formula by integrating the PDF, since the CDF is an antiderivative of the PDF. And so before we work with the next couple of questions, let's just take a look at what the graph of the CDF would look like. So over here, we have the PDF. And over here, we have the cumulative distribution function, the CDF. And so we started with a linear function. Its antiderivative, not surprisingly, is a quadratic function, at least over the interval from 0 to 4. And so what we're plotting here is if I were to calculate this area, that corresponds to this value over here. And next, we'll see how we can use each of these graphs to calculate the probability that random variable x is less than 2. So if we wanted to express this function, the CDF, in terms of a formula, we should just specify that it is equal to x squared over 16 as long as x is between 0 and 4. And when x is bigger than 4, so when we're on this piece of the function, now we've reached the maximum value. So the cumulative distribution function is going to equal 1. And this is going to be when x is bigger than 4. And we don't have it graphed over here, but since x is, its minimum value is 0, then the probability, any probabilities for x being less than 0 are going to be 0. So we actually have this piecewise function where the cumulative distribution starts off at 0, then it should increase as x gets larger and eventually flatten out, and as x goes to infinity, approach 1. And so we see all of these properties in our graph. Okay, so now let's say we want to calculate what is the probability that x is less than 2. So one way that we could do this using the PDF would be to calculate this area, and I'm going to delete some of these drawings, would be to calculate this area right here. So we could calculate the value in 3 by integrating from 0 up to 2 the PDF function dx. And so this is going to tell us the area of that triangle. So we could calculate that area doing 1/2 base times height, or we could calculate the antiderivative and then evaluate the difference from 2 to 0. So this would give us 2 squared over 16 minus 0. So we actually get 1/4. And we could also calculate that, since we found the formula for the CDF over here, we could also calculate that by taking and evaluating the CDF at the value 2. So this tells us the probability that x is less than 2. And so in this case, right, we get the 4 over 16 equals 1/4 when I plug x equals 2 into the formula for the CDF. So either way, we get 1/4. So that's, I don't know why I plotted the point at 1. That would correspond to this point right here, which is right at 0.5. Okay, so next, if we want to calculate the expected value of random variable x, then what we need to do is evaluate the integral from negative infinity to positive infinity, which means minimum value of 0 up to the maximum value of 4 for this random variable of x times the PDF. So the PDF was equal to x over 8. That goes over here. The expected value is equal to x times the value of the probability density function. So it's another integral. We integrate over the entire domain of the random variable. So now we would integrate from 0 to 4 of x squared over 8 dx. And so this comes out to x cubed over 24 from 0 to 4. And that gives us 64 over 24, which is approximately 2.667. So the expected value of random variable x is somewhere between 2 and 3, about 2.667. So I'll mark that right here. Then lastly, in 5, we want to calculate the median value of this function. So there are two ways that we could do this. If we have the PDF, recall we'd want to calculate the median value is the value of random variable x such that all of the area to the left of it is equal to 0.5. So we could integrate x over 8 dx from 0 up to m and set this equal to 0.5 and then try and solve the resulting equation. So this would give us, when I integrate that, x squared over 16, we evaluate that from 0 up to whatever the value of the median is, and this would give us median squared over 16 should equal 0.5. And then solving for m would give us m squared is equal to 16 times that 1/2 is 8. Therefore, m is equal to the square root of 8. And this square root of 8, since you might not think about values in terms of square roots, is approximately 2.83. So that would be just a little bit further over here. So notice that the median in this case is 2.83, and the mean, we calculated the expected value to be 2.667. So they're close, but different. So there are different ways of measuring where the data is centered. And this is telling us that right here, all of this area is approximately 0.5, and that means the rest of the area is the other half over there. So this value that we found, the 2.83, perfectly divides the area in half. And that corresponds to this value right here. So if we had the CDF function, then it's actually much easier to calculate the median, since all we would need to do is set that CDF function equal to 0.5 and then solve. So that's the same equation that we got over here, just we didn't have to do the integration because we've already done the integration when we found the CDF. So that's an example where we have a continuous random variable, and so we were able to think about the graphs of the PDF and the CDF and then use those graphs and formulas to calculate things like probabilities and expected values and medians. So we'll kind of discuss this at the start of class to see if you have any questions, but good luck practicing this on the quiz.